Hi there, Dr. Fox here on this next in a series of lessons from the AQA A-level physics course, and this is the astrophysics unit. We're going to be dealing with Doppler shift today, mainly to do with either redshift of galaxies receding, or primarily to do with the detection of exoplanets. And this is also a great little bit of the qualification here, is that how to detect planets around other stars, and also how to detect the physics of binary systems of two stars going around each other as well, but primarily exoplanets. I'm going to deal with both. Now, in the specification, binary stars are mentioned and then exoplanets are mentioned, but the physics is the same of how you determine the radial velocity, the radial size, the year, effectively, of either a system that has planets around it, so a central star with a planet that's unseen, or binary stars that have got a star here and a star here that are orbiting a common center of gravity. And often you're only really seeing one of the stars. So it's the same physics. It's basically one thing orbiting a common center of gravity, and we're seeing redshift in the emission that comes from one of them, or both of them, but generally from one of them. So I'm going to put these two physics concepts into one, but I'm going to give you some practice on exam questions on how they look differently, and also get you familiar with this redshift equation, which is really very straightforward. The redshift equation is easy. It's just change of frequency or divide by frequency, or change of wavelength divided by wavelength. But nevertheless, it's still worth knowing that it occurs in two places in terms of orbiting. So binary system, two stars, or a star with an unseen planet. Redshift also occurs, like I've mentioned before, with the Hubble diagram. Recessional velocity comes from that, and I'll mention that as well. So this is all about Doppler. It's about stuff orbiting each other. It's about things moving away. It's the same physics, but I'll try and get it into context throughout. So in your notes, get your notes out. Doppler effect, binary systems, and exoplanets. The Doppler effect in general, you would have done this multiple times through Key Stage 3 and Key Stage 4. I'm just going to just recap what that is, only briefly. To be able to apply a Doppler effect to optical and radio frequencies, it's very specific in the specification. It does say radio frequencies as well. Haven't seen any questions about that in radio frequencies, so you never know. To be able to interpret data on a binary star and exoplanet system, so they're going to be given graphs like we've got here. This one is a this isn't it's a Doppler one, but nevertheless, it's still in understanding different data, giving you different things, and then calculating the rotational speed. So there's lots of techniques of detecting exoplanets, binary systems. I'm going to show you exactly which one you use and when. And it's important to realize the differences between them. So this is going to be a reasonably detailed lesson, which you do have to concentrate. You'll probably have to stop, rewind, and go through what's happening again. And these equations, of course, here is giving you a formula sheet, so don't sweat about remembering these things. You just have to remember what they stand for. Z is redshift in every context. Okay, so exoplanets and Doppler shift. So there's a satellite that was sent up, Kepler, is looking for these things, and it tried to detect planets. And pretty much every star we look at, you can detect planets around it, which is pretty extraordinary, and hopefully gives us an idea that the solar system is not unique, although there is some aspects of the solar system that do seem quite odd compared to what we've seen elsewhere. But importantly, why is it difficult to detect planets orbiting other stars? Because they're dim. They're a long way off. You can't see them. They're outshone by the main star. You can't detect exoplanets directly. You can't take a telescope and try and look for it. You can try and blank out the main star, but it's extremely difficult to be able to do that because the only light that comes from them is one that is reflected. There is techniques to be able to work out what the atmosphere of these planets are and things like that, and it's really clever, and the work in lots of universities to try and work out what these planets are is, of course, one of the biggest questions. Is there one that's likely to be Earth? And what is the likelihood? Pretty high, actually, because there's billions of planets out there. There's 100 billion stars in our galaxy, and there's 100 billion galaxies. So there you go. Even if it's 1 billion to 1, we've still got billions of Earths out there. What has Goldilocks got to do with it? Go and look up the Goldilocks zone. Go and look at that. I'm not going to do it here, but go and look it up. It's extremely interesting, and the Drake equation as well. Go and look that up because it's all really interesting stuff. But this is sticked into the A-level one, so we needed to be able to work out these techniques. What's the physics of being able to work out whether or not there is a planet out there or not? Okay, so Kepler-20, I say this, but I say Kepler-20 has got the most planets detected around it so far, but I say this, and there's bound to be another one now. What this says behind my head here is how can we detect so many planets so far away? Kepler-28, which is a G star, just like the Sun, seems very strange. It has 5 planets that are all orbiting within the orbit of the equivalent orbit of Mercury, and you can see there's medium-sized ones, there's big-ish ones, quite small ones. This is Mercury here, and it's odd, like really, and they're orbiting really quickly as well. So it seems like a lot of planets are quite close in, and sometimes they're the size of Jupiter, and they're really close, and they're called hot Jupiters that are going round. So solar system seems odd as having a Jupiter-sized planet quite a long way off, and some rocky planets all spread out. This could be a feature of just how we observe this stuff, how we observe these. There could be many more all the way out. There could be hundreds of them, and we just don't have the sensitivity to be able to do it. But it doesn't look like that's the case. It does look like we've taken everything we can. But anyway, there's 2 things here. There's something called transit method, and there is something called Doppler method, which is roughly behind my neck. And I'll go through both of those of how you detect exoplanets to start off with, and I'll make it very clear when we're detecting exoplanets and when we're detecting binary systems, i.e. 2 stars. Exoplanets is when there's a star and just planets. Binary systems is when you've got 2 stars. One is often very much bigger than the other, but I'll make that distinction. So transit method. This is exoplanets. So this is when we have the unusual circumstance. We have the planet and the star the planet passes in front of the star. And this happens with Venus, of course, from the Earth. You see the transit of Venus across the Sun. And this can happen on other stars. And if you look at a star for long enough, you can detect a dip in light output because, of course, this planet is occulting. It's going in front of the star. And, of course, the brightness goes dip. And this is from ground base, and this is from Kepler, which is the satellite which I showed you. And you can see it's much better from space. This method works. However, it only works if your planet is lined up with a star. You have to look at millions and millions of stars all at the same time to be able to work out whether this light curve is happening. Of course, it happens relatively slowly, usually. However, now we realize that a lot of planets just whip in front, so we're not going to be able to do it. So this is a method. It's not a very good method, mainly because you need to have these unusual circumstances, and also these difference in brightness, in magnitude, in output, and intensity. All of those things, they just dip fairly quickly. I mean, you can get a lot of information. For instance, you can get the radius of the planet. You can get ideas about what if you take a spectrum here, you can actually try and detect what's in the atmosphere of the planet as well. You can see, you get ideas about the radius, about the speed of the orbit as well, and therefore you end up getting this thing. That's the transit method. That's the light curve of a transit method, and you can see how that works. Now, the Doppler shift method, which is called the radial velocity method. Now, that term doesn't really give you an idea, because radial is basically outwards from the center, as in following the radius, and velocity means it's moving. However, this actually involves a planet orbiting a star, and then the star actually being wobbled backwards and forwards by the planet and the star orbiting a common center of mass. So this is the star, as you can see this little diagram here, really good. The star is actually moving around a little circle. It's probably not moving an actual circle. It's probably just, that circle is probably within its own radius. But nevertheless, it is being forced to be wobbled by the planet that is pulling it out of its orbit. So as you can see, we're not detecting the planet directly. We're detecting the wobble on it here. And from this, we can work out a number of things about the orbit. So when the star, you can see on this picture here, when the planet is moving away, the star is moving. I was right first time. When the star is moving away from the Earth, you can see that at this side of the orbit here, it is redshifted the most because it's receding the quickest. And then when it's coming towards, it'll be blue shifted. Now, importantly, there are 2 positions in between as well where there's no redshift or blue shift. When it's going across the field of view at the nearest point, and when it's going across the field of view at the furthest point. There's no Doppler shift there because it's neither going away nor going towards. Redshift when it's going away, blue shift when it's going towards. Remember, it's just orbiting a small radius that's being pulled out of this radius. out of its orbit by the unseen planet. This is a more typical graph to look at. This is the velocity here, up and down, and this is orbital phase. So if you measure a wavelength of a particular absorption line or emission line from a certain transition of an electron in the outside of an atom in the star, then that line will be shifted backwards and forwards depending on where it is. It will be shifted to long wavelengths when that star is moving away, then be shifted to shorter wavelengths when it's moving towards. And you end up with this, a sine wave. And from this, you can, of course, get the orbital period, because from there to there, for instance, or from there to there. And you can get all those things. And we're going to do those calculations. And those are the things that you need to be able to learn for your A-level. The other one is eclipsing binary. So we're going to go back to a transit method here. So the other two were all for planets. This is for now binary. So we've got a large star with a small star now that's orbiting it in the plane of view. So we're seeing going front and behind. Now in this case, instead of it just transiting and going down, and then that's all we see, there is two transit periods and there's two dips. So this was relative brightness. So whatever it is, this could be 4, for instance, of a brightness of a star that's just about visible by the naked eye, if it's apparent brightness. So when the star is off to one side, it's full brightness. You're getting full blast from both stars. Now, when the star disappears behind it, you lose all of the output from that small star. And it goes down here. So the brightness dips, and it comes back up again when it appears. There it is. And then when it goes in front of it, it dips a little. Now, you might think, what? But actually, it's because this star is just occulting. It's just blanking out that little bit of the star there. And therefore, there's a little bit less. And then, of course, it does it again. And you end up with this two-phase, deep, shallow, deep, shallow. And, of course, then you can work out what the relative emission from each of these. Of course, this here will just be the emission from from this star here, because the other one's gone. And, of course, this distant difference here, of course, will tell you a little bit about, the brightness of the secondary star, the smaller star. And of course, this here, of course, the length of this is incredibly interesting. This tells you how long it takes the star to get from there to there, and from there to there. So, it should be the same, because that's the star going round, but nevertheless, it's still interesting stuff. So you can tell a lot about it. You can work out the radius, you can work out the radius of the star and the orbit time, lots of. And these, and this is where we get, this is what it looks like in the exam, basically. So this is what they give, apparent magnitude down the side there. Notice how this goes. Remember, this is getting brighter, this is getting dimmer, time in days, and therefore you've got lots of different parts in here as well. And usually it's that way around. I know it's crazy. You just have to get used to those axes and brightnesses. Okay, what can be determined from these data? Just as I mentioned before, orbital period, size of the main star as it goes across, and also by the rate at which this goes down, because this is not vertical. You can actually work out the size of the smaller star as well. Incredible stuff. You've never been, but yeah, that's what astrophysics is all about. Your laboratory is trying to work out basically a detective story from the evidence that is left over. Now, here we go. This is now a binary data. I said in the learning objectives we're going to look at data. So in this case, this is wavelength. So we're going to take, this is a wavelength of a single line. It could be an absorption line or an emission line. The middle of this, of course, this is what you'd expect if that emission was taking place on Earth. In other words, unredshifted or unblue shifted. When it goes up here, of course, this is when it is maximum redshifted. What's this? The peak at which it is maximum redshifted. That's when either the binary system or the planetary system, that's when the star is moving away the quickest. So this could be either. So this could be exoplanets or binary. In other words, that's when that star is moving away the fastest, not when the planet's moving away, or the other star, when that star is moving away the fastest. And then it's going away. Go. So yeah, it's going around on there, and it's coming up on there. So this is when it's going fastest further away on one side of the orbit, and then it's coming towards on the other side of the orbit. And then it says, draw a sketch of the section which applies to which part of the binary system. So you'd have to draw two stars going around each other, or a planet going around each other. It doesn't matter, because actually, the case in this case, you're looking at one star's emission. So we're going to get some calculations done here. So I've just drawn here the central star. So basically A and B is the same star orbiting a very exaggerated center of mass or center of gravity, but just to make it really obvious. So you can see that on the blue side, B, is the redshift. Should have changed that, shouldn't I? On the B rather, that's receding, that's the redshift. On the A side, it's coming towards you. And that's redshifted red and blue. So now I'm going to get that data that I showed you before and work out here. Now, this is the equation you're going to have to use here. So this is the change in wavelength, which is the change in wavelength from unredshifted or unblue-shifted wavelength. And this is the unredshifted or unblue-shifted wavelength. This is the wavelength you get if you were sitting next to it on the Earth. So this change in wavelength is the difference between here and here. And this is this line here. Both will be measured in meters or nanometers because it's a ratio. Velocity is what we're looking at, the approach or the recessional velocity. And here is the speed of light. So our only unknown, of course, is the recessional velocity. That's the 1 minus sign. And as it's going away, if it's blue shifted, of course, it will be a positive one. So work out the difference between here, and here. You'd have now to peer at the screen quite closely to be able to work out here. That says 34 and that says 28 there. So the difference between there, it's only very small differences. Then pause the video and then I'll show you the answers. 3, 2, 1. Here we go. So the difference between is 565.28 minus this one, and then that's the unredshifted one, and that gives you a recessional velocity of about 32 kilometers per second. Getting the idea that that's about the right number, 32,000 meters per second, which is pretty quick, which is what you expect from planets that are doing little wobbles in there. Typical, right? So now we can use this to calculate the diameter of the orbit. Distance equals speed times time. So we've got the speed now, the recessional speed. Now from here, you work out how long it takes to get from here. Now this is a full orbit, so we're picking any part of these, which is the same. So from here to here, or from here to here. Have a look at the diagram, work out how many days, and then convert into seconds, of course, because that's what examiners do. They go fishing for the people that don't spot their units. And therefore you end up with an orbital diameter in meters. So do that, and I'll show you the answers in a second. 3, 2, 1. There it is. Oh, what a shit. I just put it behind my head. Anyway, distance equals speed times time. Circumference, orbital speed times orbital period. There you go. That's our answer from the previous slide. 8 days, 24 hours in a day. There's the number of seconds in an hour. And therefore you end up with that. All this is here is the diameter divided by pi to be able to get you the diameter of it under there. There it is. Do it yourself and find out what that number is. I can't remember off the top of my head. Well, there you go. There's the that's all the calculations you can do from this. Now remember, this can be binary or exoplanet. It doesn't really matter. You're just working out the how the orbital period of that. Okay. Right, here we go. So 999, a planet was discovered orbiting a star in the constellation of Pegasus. Step 1, reason why it's difficult to direct observation of this planet, just as I said before, direct observations of the planets. You can't see them directly because they don't give out enough light. They're dim, they're outshone by the nearest star, so put those into your own words, please. Initial discovery of a planet was made using the radial velocity method, which involved Doppler shift. With respect from a star, explain how orbiting planet causes Doppler shift. You have to just describe the fact that they're orbiting a central center of mass. 2 marks for that one. Discovery was confirmed by measuring variation in parallel. Explain how an orbiting planet causes a change in the apparent magnitude of a star. Sketch the graph. So in this case, they've asked you about both. So the bottom one is the transit method. Hasn't mentioned the word transit, by the way, and the top one is about Doppler. So you can see how the measuring the dip in it as well. So there you go. There's 6 marks there for everything. Basically, they're going to ask you about exoplanets. Now, when we were doing the calculations before, if you're doing the orbital velocity, remember the velocity is of the receding star orbiting a center of mass. So just be careful. You're not getting the orbital radius of the planet in that case. That's just the binary system star. However, you can work out the recessional velocity of the star of the planetary system, not the planet. So remember, when you're doing all this stuff, you're only ever measuring stuff to do with the star, and by inference, the planet is discovered. With binary star systems, you are actually measuring the recession velocity and the approach velocity of a binary system. So just be wary of those two methods. The Doppler system is used for both, whereas in a binary system you can actually detect radii because that's the actual velocity of that star receiving. So, but this question here is purely about planets. So it's just asking about those two methods. Okay, and there's the answers. So there you go. All the stuff that I went through there. Star much brighter, common center of mass, and then with a dip, and then make sure you got that dip identical to the one we've got. Now, this is a question that wasn't from AQA; it was from elsewhere, but involves something called a binary system that has two systems going around like this. So it's very similar to what I had before. You can see here that the Earth is in this direction. The direction of rotation of the star is here, star A and star B, and that's the center of mass. So therefore, this is where you're talking about shifts in spectrum of different stars. So this is, at the moment, this one here is talking about this question here. I'll read it out because we need to do this slowly. Figure 1 shows two stars, A and B, which form a binary star system. The two stars orbit their common center of mass with the same period of rotation. The Earth is in the same plane as the orbits of the two stars. But yeah, the calcium K line from a laboratory source has a wavelength of this. The same line we measured in this when A is in position in figure 1 has a wavelength of this times 10 to the power 7. Calculate the velocity of the binary star system. So you can see they're telling you which of the different parts of the position is in here. Now this one here you can see is a significantly larger number than here. So this is when it's in when it's coming at Q. P of course is when it's receding here. So this is a larger wavelength. So this is when it's going to be going into position P, which is hidden behind my head in there. Okay, and so therefore you can do the calculation there. Calculate the velocity of the binary system. Of course, you've got your difference in wavelengths here. Calculate difference in wavelengths. Difference in wavelength divided by wavelength equals velocity divided by speed of light. Stick all your numbers in and you get your velocity of the binary system. And there you go. And that's it. And it's moving away from the Earth, of course, because your wavelength. Here's another system. This is an eclipsing binary system. So this is not a planet this time. This is a star that's going in front and behind the system. So this is the other transit method, which is binary stars. So HT Cassiopeia, which is an eclipsing binary system, the constellation of Cassiopeia, shows a variation of apparent magnitude like the system over a period of time. And this time they've given it this way up. They don't always. Apparent magnitude, so therefore this is getting brighter up here because the number is getting smaller. This is in minutes, notice, that's always worth looking at. This does not go down to 0, but this does go down to 0. So that you can measure a lot from here. Explain how the motion of two stars produces light curve in figure 1. Refer to regions A and B in your answer. So therefore go through the idea of the star going in front and the star going behind and the different depths of those to be able to do it there. Good quality. This is probably between 4 and 6 marks, depending on the exam. This one was 6 marks particularly, but it could be. It could be anything between there, depending on the examiner's what sort of mood they're in. Okay, and then here we go. Analysis of the spectrum of the system shows that one star is moving with an orbital speed of 400 kilometers per second. The wavelength of the hydrogen line, so this is the emission line of the spectrum of stars, an average value of that, so that's the middle. Recognize that number. Calculate the maximum and minimum values of the wavelength of this star due to the star's orbital motion. So therefore we need to go the other way in this case. We've been given the recessional and approach velocities, so we need to measure two changes in wavelength. And that change in wavelength there comes from the fact that the delta lambda is derived from, we know this because it's given here. We know this because it's on the formula sheet, that's the speed of light. And we've been given this in kilometers, so we need to convert that into meters. We need to convert the nanometers into meters as well. We get change in wavelength, we need to add and then subtract from this number here to get the maximum and minimum values, one with the red shift, one with the blue shift. Using figure 1 to obtain a value of a period of the binary system, and calculate the radius of the orbit of the star. So just rewind the video, have a good look at that. Have a good look at the radius. Remember, it's the same thing you're measuring to on that, and then calculate this. And I'll show you the answers. Pause the video. I'll show you the answers in 1, 2, 3, and there they are. Okay, so there we are. We've got the full explanation. 1, 2, 3, 4, 5. It was out up on this one. It says maximum 4, but it could be a 6 marker. And 7b, which is the one that I had before. Minimum wavelength is there. Maximum wavelength is there. So a little bit above, a little bit below, and then of course you end up with a period there. Sorry, a radius there of 4.2 times 10 to the power of 8 meters, which is 100 million meters, which is about right. Okay, for a binary system. So there you go. Pause the video if you need to do that again and look up and try and work out what on earth's going on from the mark scheme. But the mark scheme is really quite good, quite complete. So we've done this one here. So I've only shown optical frequencies or wavelengths rather, but it could come in frequencies as well. And you can notice in the formula sheet, delta F over F is the same thing. The only difference in this case, of course, is that frequency will be lower for redshift and it will be higher for blue shift. So just be wary of that. Never seen that in an exam book, just be wary of that. Calculation of binary stars viewed in plane of orbit, just like the ones we've been to. Binary stars, just one binary star, remember, that you're looking at. When it's an exoplanet, you're looking at the star and it's just a wobble. You don't know much about the radius. That's beyond the scope of A level. And then just to go back to this, you need to know light curves of each of those systems and the detection techniques, which were limited through a Doppler shift. And the transit method. So there's 2 transit light curves you need to know. 2 transit light curves. One of a planet, which is just a single dip. The second is an eclipsing binary system where there's 2 dips, one small, one deep. And then the Doppler shift method is either the star with a planet being wobbled, or you've got the binary system where one is receding and one is approaching. So there's quite a few scenarios where you need to use Doppler shift. Be wary of which one you're using. This one is one of the hardest bits, I think, of the astrophysics course from a conceptual point of view. Mathematically, it's really quite straightforward. But as long as you get your head around those different scenarios and where you use the physics, then you're fine. Go and watch the video again. And then we'll move on to the next stage, into the final straight.